Hey guys, welcome to Analytics Vidya. Idea behind doing this video is to give you a first-hand experience of how to get started and perform hands-on with the leading open source generative models using the free T4 GPU on Google Colab. In the last 1 year, the world has been wholeheartedly appreciative of ChatGPT and all the cool stuff we may do with it. But all this while, there's been a silent revolution that has taken shape and is now ready to disrupt this whole domain of generative AI. This silent revolution is nothing but the emergence of more than a handful of open source models that have been released into the public domain. Some of these open source models have even beaten or gotten fairly close to GPT-4 on certain task-specific use cases like code writing. So in this video, we are going to perform hands-on with 3 different open source generative models: Dolly 3 billion model released by Databricks, Falcon 7 billion model released by Technology Innovation Institute based out of UAE, and Stable Diffusion version 1.5. To ensure that all of us are able to follow along, we'll be running all of these models on the free version of Google Colab using their free T4 GPU. In fact, that's the precise reason why we have chosen these smaller sized models so that we may do our inference seamlessly. Yes, smaller models means deteriorated performance, but the idea here is to know the possibilities rather than pursuing perfection. Makes sense, right? Just one last thing, guys, do us a favor by subscribing to our channel. It's absolutely free for you, but it motivates us big time. So please do that. Now let's jump on to the hands-on. Alright guys, this is the Google Colab notebook that we'll be reviewing in this video. As you can see, I have already documented the code for Dolly 3 billion, Falcon 7 billion and Stable Diffusion version 1.5 in this particular notebook, along with some details on the models. So let's start with the first model, which is the Dolly 3 billion model, which has been released by Databricks. And before we get started, let me connect to our T4 runtime. These are the steps to do this. So this T4 GPU we get for free as part of Google Colab, but there are some limitations on its usage. So do read about that when you get started. All right, we are connected to the runtime now. So here's a bit about Dolly 3 billion model before we actually get started with the hands-on. It's an instruction-tuned model that we are using, having 3 billion parameters. And this is the link to the Hugging Face documentation that you may refer to. All right, so I'll leave this particular part to you. Coming back to Colab, for pulling the model from Hugging Faces, we are going to use their Transformers library as we are installing this here. This library provides APIs and tools to download state-of-the-art pre-trained models for performing hands-on within our system environment, which is Google Colab in this particular case. Additionally, we are using sentence pieces, which is commonly used for text tokenization use cases in natural language processing, and accelerate, which allows for faster GPU computing in machine learning. Don't worry too much about these two, so I'll just install them. All right, once the installation is done, then we are importing these bunch of modules. PyTorch, which allows tensor computation with strong GPU acceleration. Our Transformers pipeline, which is the fastest way to use pre-trained models for inference, and OS, which is a standard Python module. So let's go ahead with this. Thereafter, as third step, we load the model using the pipeline function, which is this. For this, we create an instance of Dolly pipeline. This is the model that we are specifying. So this model name is basically the path we are declaring to this particular page. Moving on, this next line sets the data type used by PyTorch to process data. Torch.bfloat16 represents the 16-bit binary floating point data type. Using a lower precision data type like bfloat16 can speed up neural network computations and reduce memory usage. Thereafter, this trust remote code equal to true. This setting allows the pipeline to trust remote code that will be downloaded into our runtime environment through pipeline. And thereafter, this device map equal to auto. This line specifies the device map for processing. Auto typically means that the pipeline will automatically select the best available hardware, either CPU or GPU, for processing based on the system's capability. In our case, we have a GPU available in our Colab environment, and that will be mapped and utilized. So let's initialize this. And guys, this model downloading part may take around 4-5 minutes, so please be patient while this happens. Alright, now when our pipeline is ready to be consumed, next up let's define a helper function that will allow us to prompt the Dolly model. For this, we are defining a function called getCompletionDolly that takes one argument as input. Within this function, this is how our prompt is structured. It has a system instruction, then the user input, and then there is a placeholder for the model to generate its response. System instruction is basically this: you are an expert physicist, you are good at explaining physics concepts in simple words, help as much as you can. So basically we are asking our Dolly model to act as an AI physics teacher for us, and with the user input we'll be asking some bit of physics related questions and see how the model performs. All right. And within this helper function, we are also printing the prompt, the final prompt, which is being compiled and is fed to the Dolly pipeline for generating text. And finally, we are calling this Dolly pipeline that we created above to generate response on our prompt. And as output, the helper function returns the model response. Let's initialize this function now. All right, now comes the exciting part where we are going to prompt our Dolly model. So let's begin. The first prompt that we have is this: explain the difference between nuclear fission and fusion. So let's see what we get from Dolly model. So this is the printing part of the prompt that our helper function is doing. And this is the response that is generated by the model. Nuclear fission and nuclear fusion are two distinct physical processes. In fission, an atomic nucleus will split apart into smaller atomic nuclei. In nuclear fusion, two or more atomic nuclei will fuse together to form a large atomic nucleus. So this seems like correct. And even in terms of the structure, the response is pretty much up to the mark. What do you think? Now, I'm sure you would start thinking about what you could do with this power that you possess now, all for free. For that, I have a small glimpse to share with you as to what all is possible. Now, on top of this Dolly pipeline, let's build a generative AI application using Gradio. For this, first of all, I'll install Gradio. If you face this kind of error message, then this is the code that I have kept for you. Basically, you need to change your locale from this to UTF-8. For doing that, all you have to do is to run this particular line of code and it will work. And now if I try installing it again. Talking about the Gen AI application, we are going to build an AI physics teacher application. You may ask whatever physics related question that you want this app to answer, and the app will give you well elaborated answers. Now Gradio is installed. Next step is to write the code for the app. So basically this is the app. We are using the Gradio interface, and within this we are pointing to our getCompletionDolly function, and input is basically the physics question as prompt. Output is the answer from the model, and title of the app is My AI Physics Teacher, and then few examples that we have added within the app. Now let me just launch it. This iface.launch is gonna launch the app for us, and share equal to true is basically going to give a link that is active for 72 hours, and within those 72 hours you may share this particular link with your friends and family, and they will also have access to your app that you have built. Cool, right? So this is the app. Now you may try giving some physics questions to it and see how the model behaves. You may input whatever physics related question that you may have. For this demonstration, let me go with the same question that we asked the model a while back, and let's see what we get. And as you can see, the model is explaining the two physics related phenomena. And as you can see, the model is able to explain the two phenomena. So this is all I had on the Dolly model, guys. Now, similar to this Dolly hands-on, you may also perform hands-on on the Falcon 7 billion model. In fact, I've kept this ready to use code for you in the same notebook. I'll share a link to this notebook in the description part of this video. Just make sure that you restart your runtime from here before you get started with the Falcon 7 billion hands-on. Within this section of code, more or less everything remains the same. You are installing these particular libraries, then you are importing them, then you are loading your model configuring your Falcon pipeline, and thereafter again you are defining a helper function get completion Falcon this time around, and post that you can start prompting this new model. The version of Falcon that we are getting to use is 7 billion parameters, so definitely the responses should be better than the Dolly 3 billion model. Whatever your evaluation is, assessment is, do let me know in the comments section of this video. There's one model still left, which is the Stable Diffusion version 1.5 that I'll be covering in the second part of this video. So do look out for that next week. If you haven't subscribed to our channel yet, please do it now so you get notified whenever the Stable Diffusion hands-on video is live. Happy learning to you. Bye.